Hi everyone, good morning. My name is Dean DeLeo. I'm a PhD student at the Centrum Wiskunde et Informatica. I hope I pronounced it correctly this time, in Amsterdam, under the supervision of Peter Bones. And what I'm going to present is our effort to extend MonetDB and to provide shortest path queries on top of that. So, okay, we have a short agenda. Okay, I'll give an introduction, what's our purpose. Then I'm going to describe our extension to SQL, how to perform shortest path queries. In a way, we'll see shortly. I'll sketch a bit the implementation, and then the final conclusions. What I won't provide you is evaluation results at this stage, because it's still an early stage, it's work in progress. Okay, so this is part of a Dutch project, Graphalizing for Security, which has the purpose basically to study the platforms or algorithms or data structures to perform analysis of graphs that are continuously updated. It involves three stakeholders. One stakeholder is a company called OB41, which they're going to give a talk tomorrow morning, I think. So you'll hear from them directly. The second stakeholder is LDVC, which is interested to understand how effective are their benchmarks. And then there is the third stakeholder, which is the CWI Institute. And for our purpose is to extend MonetDB. Do you know what MonetDB is? Can you raise your hand if you don't know? Okay, yeah. Oh, okay. So MonetDB is a relational database. And it's a database management systems, okay? It's a column store, it's open source, and it's mostly tailored for analytics. And you can guess who is the main contributor to this database, CWI. And so our purpose is to extend this relational database to perform shortest path queries, and we'll see how, what does it mean, what it means. And then eventually also to evaluate the products, the final products with the extensions on top of the SNB, social network benchmark, interactive workload defined LDBC. Okay, so we started with a description of our extension. So remember that this is a relational database. Here we have tables, we don't have graphs. And operators apply on tables and table expressions. And what they give back are tables. This is a strong point of SQL and relational databases. But then we want to define whether two nodes, whether two entities are connected. And in a graph, it means that two nodes are connected if there exists some kind of path of finite length. Here, we don't have a graph, but we can implicitly define one by using a table and assume it has two attributes, which I call E from E2 in this. And we implicitly define a directed graph where the nodes are the unique values. It's the union of the values between the attributes E from E2, and the edges are actually represented by the actual tuples that are present in the edge table. And in this way, we can express whether two entities are connected over this table. And this is a sample. This is our extension where we introduce a sort of join predicate. So the first part is the select from, I assume you already know. This is a self-join between the tables V1 and V2. And the extension is the blue part, where we ask whether V1 ID can reach V2 ID, over this edge table E from E2. So, and the predicate, this is a joint predicate, is satisfied whether there exists a value from E from that matches, that is equal to V1 ID, and a value from E2 that is equal to V2 ID, and then there exists some finite path over the graph that is implicitly defined. Sounds scarier, but in practice it works nice. And I'll give you a sample. So this is, well, this is the person, and if you take the LDBC data generator, you have a person and a person's entity, and then a person knows person's relationship. And this can be represented as tables, as two tables, person and friends. And if you consider that friends are, well, usually you have that if a person A is friend of B, then you also know that B is also a friend of A. I guess makes sense. And so this is why you usually, since we assume that this is a directed graph, we duplicate the tuples to express this friendship relationship. And so here I want to perform a query whether Mahinda Pereira is connected to Carmen Lapland. And so I perform a self-joins between the two persons, where the first person is Mahinda Pereira, the second person is Carmen Lapland, and then I describe this I introduce this joint predicate whether Mahinda Pereira reaches Carmen Lapland according to the relationship defined by the edge table, which is ID1, ID2. Now, to stress that these are table expressions, if I want to restrict whether they were, for instance, they knew each other before a certain date, in this case, the 1st of April 2010, I just modify the table expressions that defines the edge table. And I do this through a with subclause. And I'm changing the edge table in this way. Okay, so this is how we express reachability, whether two persons are connected, two nodes are connected. But then we might be interested, when they are connected, what's the minimal distance? What's the cheapest, what's the minimum cost of this connection of the path that connects these two entities? So the point is that this joint predicate, T1 ID reaches T2 ID, it acts like you can express expressions in the, like summaries, in the select clause that give you a way to compute the minimum distance according to an expression that is bound to the edge table. And since we have also the distance, we might also be interested in what is the actual path. And here the path is the sequence of edges or tuples that describe the path that has been computed to define the minimum distance. Again, giving a sample. And the problem is this path is a sequence of tuples in the way I define it. And here you have a single tuple as a result. Well, for each matching tuple as input. So, but the path, since it's a sequence, it might represent multiple tuples related to a single tuple from the input. And the way we represent it is introducing the concept of nested tables. And so nested tables are this kind of, are basically, are containers that include tuples But if you want to manipulate them, you need to bring back to the what SQL understands, which is tables back. And we do this through, this is a solution already introduced by other products. Basically, we introduce this new keyword, flatten, which joins each tuple in the left-hand side, so that comes from TMP, in this case, with each tuple of the related nested table. Yeah. Again, with an example to clarify this. So let's assume we have this as input as this table rows. Will be our edge table. We want to compute the minimum, the fastest path between the segment 1 and the segment 4, according to some criteria. And here the criteria is the distance divided by the maximum speed of the segment. And so I remind you that the distance and max speed will be evaluated in the context of the edge table. And yeah, and we also want to know, besides what's the time to perform this, what's the most advantageous time to perform this distance, also what are the actual segments that compose it. So when we perform this query from segment 1 to segment 4, we return the result according to this table will be, okay, the matching tuples, the time to perform it, and then this strange beast, which is the nested table. Now, you cannot manipulate as it is. You can only project or forward to the other operators. But the key is that you need to flatten, you need to expand it, and to this additional operator, where where the left-hand side, so the tuple from that was resulted, is joins to each tuple of the nested table, and then you're back a table. You can operate as it is with the other operators from SQL or from the relational algebra if you're into that. Okay, so just to conclude, so the first part on the SQL description. So here we don't have a statement to build a graph. The graph is implicitly defined by this edge table where you have two attributes, and they must have the same type, and then you can define the graph according to the values of these two attributes. The entities involved, there is no particular object that represents a path. There is no particular, there is an object that represents a path, but it's a nested table. And all the other entities are, again, table expressions, so are common tables. In general, this syntax allows you not only to perform the cheapest, the shortest path among single values, but since it follows the same join predicate syntax, it allows you to compute many-to-many weighted shortest paths. It's also good to point some limitations, is that you can restrict, you can modify what is the edge table, because this is a table expressions in the way we did before, that we wanted to know whether two friends were knew each other before a certain date. But what you cannot do, and actually several other products allow you, is to specify conditions that depend on the path. So I want a path where the first node is, the first edge is black, the second edge is red, etc., etc. So this is a path-dependent condition. With this proposal, you cannot do it. It's a limitation. And there are also some edge cases where the syntax is non-trivial. This is a sample. where here you have, again, this self-join, where the first part is this new join predicate over a graph, and then you have a second predicate. And the join is satisfied whether the first or the second predicate is true. But since this is the first predicate, as a side effect, can compute a path, sorry, a cost in this case, you might introduce a new attribute. The point is this, that this attribute will be evaluated whether, if both conditions are true, it will be present whether the first or the second predicate is first evaluated. This is a bit of a tricky case. Okay, so that was the proposal. We implemented that based on top of MonetDB, the relational database I was mentioning before. Currently, we implemented this reachability clause, these join predicates, and also the possibility to produce shortest paths. Sorry, to return the distance of a shortest path, while currently we're working to add also the support for nested tables path. Okay. So just to sketch the implementation as it is right now, you get a query, you introduce a new operator, let him play in the relational, in the query rewriter and the optimizer, and then I remind you that the graph is built in our runtime. So firstly we map the attributes that describe the edges, whatever types they are. There might be even multiple attributes to the values from 0 to the cardinality of the nodes in the graph. And then we build the graph in a way that I'm shortly described. Finally, once we build this representation on the graph, we execute the shortest path operator as usual. So for the graph representation, so assume these are the edge tables, so it's a sequence of edges, and what we perform is that we want basically a compact representation of the graph. We sort this edge table according to the source node of the edge, and then we perform a prefix sum of it, and we truncate at the end. And I remind you that since this is a column storage, it makes sense to perform this sort of operations. And the reason is that if you want to know through this operation, if you want to know the outgoing edges, for instance, of the node with index with ID 1, you just go to the edge list, which will be E1, and at position 7, so 0, 1, 2, 3, 4, 5, 6, 7. And it tells you that node 3 is an outgoing edge of node 7, and looking also to the next value in the edge table, it tells you that if you do the difference, you know how many outgoing edges you have for that node. Once we construct this graph representation, we perform the usual algorithms. In this case, it will be a BFS or Dijkstra according to the ways that you specify. And then while joining the connected tuples, and then we project back the results as usual. Okay, so that was the current state. Regarding possibilities is that, the first thing, if you have multiple paths with the same distance between two nodes, which path are we going to return? And the current state is undeterministic, so whatever it is. So it would be nice to have also a deterministic result, that the result is always the same, according to some criteria. The second point is that we build this graph every time on the fly. But it might be also the case that we might know that we might want to pre-compute it so that it doesn't have to be built every time. And so a possibility is to introduce indices that for this particular representations of graphs. And if you're going to introduce indices, then we also need to update them. In case there are updates, we need also to update the index. And this might be a tricky problem because you need to you need to individuate all the updates that touch the edge tab, the graph representation, and then have a way to update the graph representation, being sure that you don't break the transaction semantics. Okay, conclusion. So this was what I presented is a SQL extension for to compute shortest path over graphs that are implicitly defined. I'm sorry I'm not providing evaluation results at this stage. The implementation to handle paths is still work in progress. I outlined areas of possible future work. That's all.
Are there questions?
Yes, question. Yeah. From the example where you showed the self-join and the short term, what would a select star of that query return?
Okay, so let's go back to the sample then. Whoa. This one.
For example. Well, yes.
So if you consider this is a self-join, this is a join predicate, and it would tell you that all the tuples such that this predicate is satisfied, of course. So whether there is a V1 AD, which is equal to one of the values of E from.
This is not a self-join, sorry to interrupt. It is a join between two tables.
Yeah.
Yeah, okay. So, what columns are returned? I don't.
The columns of V1 and V2, as it is.
Because in the next example, I think you show the cheapest sum, something like that, right? So, how does that, like,
Yep.
I was wondering how do the certain columns get in scope and then selected so that we can aggregate over them if they are not projected out by a select star?
Yeah, this is the side effect of computing this particular join, no? That is like when you have a group by and you perform aggregates. So it might be easier to see in this way that you introduce this in the syntax. It is introduced this new keywords that ask when you're performing this join, please tell me also what is the distance as additional column to be computed by the join itself, by the join predicate. Does it make sense? I see you a bit perplexed.
Usually you reduce all the rows in the from clause, and now you produce additional rows or values in the where clause.
So if you consider, for instance, the relational algebra, no, a join is basically a cross product followed by a select, a filter. And you know that each operator can have input and output expressions. So what we are doing here is basically consider the join as this cross product followed by selection. Usually a selection has the tuples returned, the columns, the attributes returned by a select are basically the same tuples that come as input to expression. In this case, we are making an extension to the select that they return the same columns of the select of the input table plus an additional column that is computed by the select itself. And then you can project it and give an alias from a relational point of view. Yep.
Maybe another question, since you put the reaches or the reachability restriction inside the where clause,
Yep.
do you plan to support multiple shortest paths inside one query?
Yeah.
Okay.
You can already do that. So you can express multiple cheapest sums in the same select. Yeah, that makes sense.
That's exactly what I was going to ask. I can't see how they're connected right now. There's nothing in the reaches that is used in the cheapest sum.
So this, so the cheapest sum, so you have two parts in the cheapest sum. So the first is the, oh, I'm missing the, maybe it's easier. Yeah, the bind. So, yep, the E. So you have here an edge expression, which is subtable. And then optionally, you can define an additional variable, which refers to this edge table, E. And then internally, you have an expression that is computed in the context of E. But since if you have only here a single, let's say, edge table, and you don't specify it, I know that it's going to be, we know that it's going to be bound to that variable, to that table. Yeah. Yeah.
Yeah, in your future work you mentioned deterministic or non-deterministic paths. So what exactly makes a path non-deterministic?
Yeah, because if you're going, so assume that exists a path between exists two paths between two nodes that have the same weight, the same cost. The problem is, which path are you going to return? The first or the second? So right now, there is no, the decision which path is going to resolve is an implementation detail. You don't know, and it may change every time that you perform the same query. While having a deterministic result, it means that if you're going to perform the same query with the same parameter, with the same input, it's going to return the same path.
But you're probably missing the other one, which isn't.
Yeah, but the problem, yeah, so.
Probably you should return both. Or there might be more than two.
That's,
It could be in the worst case also a million. I mean, where to stop? I mean, then you are at the top K, and then K can be small or quite large. You could do it, but it would make the language extension even harder to use, because then you have to assume that you will always get a set of visual spec. So you'll have to basically enroll in your application or in your super query that uses this, have to iterate through or select from this list of paths. So it will also impose a burden on the user experience. In many cases, you're interested in one best path, and you are I mean, if this is a some kind of weight that is like a floating point decimal number, the chance of it exactly having equal. There are use cases where you really expect only a single one to come back, or quality interested in it. So that, and then you would suffer for the extra complexity of having to deal with a list.
I think there should be a way to say, no, I don't want this one, I want another one.
Yeah. Well, then maybe pick a different cost function.
I think it's probably the same as, I mean, conceptually it sounds as the same problem as when you, for example, try to select in a typical group by SQL, when you want to select one minimum value, you also have to have specified order and then do it at once. So, but that's also the same problem that you have to basically have to have an outer query. So I think it should probably also be possible here. So
Yeah.
I don't know if it's really necessary to, if it couldn't be handled with existing constructs. I think it would be just syntactic sugar.
yeah, that's a good point.
Right. Any other questions?
I have two short questions. So one regarding the on-the-fly creation of the graph.
Yep.
So to me it looked like a CSR that would require a dense ID domain. And in the example it was a dense domain.
Yep.
How would you handle a graph where IDs are hashed values, for example?
Yep. So, okay. So I skipped the part because I thought it was we thought it was a way too much lower detail. But basically, the idea is that ta-da! Is that you get the edge table, and okay, as I said, the attributes are the nodes are is the union of the E from E2 clause, and you perform a group by on it. And the first result is that you remove the duplicates. But as a side effect, when you perform a group by, this is a bit lower than relational algebra. You also get the partition to which each tuple belongs. So in this way, you have the mapping from 0 to 1.
So you can calculate it. You can do everything with
And this is also why it doesn't matter, even if Rome was composed by multiple attributes. It's okay, it's fine. As far as because at the end it's going to compute a group I on the multiple attributes. And since those are all the attributes of the input table, it's going to remove the duplicates and give you the partition number. So that's why the mapping is done.
And for future work, we also consider to have different physical operators for different shapes of graphs. So for example, if assume you would know that the underlying topology is actually, for example, a planar graph or a road network,
Yeah.
would you use a different physical operator than you have right now?
Yeah, there's a problem from the physical layer. So not from the logical layer. So the syntax that is posed to the user would be the same. But yeah, at runtime, as I said, for instance, already we select whether to perform a BFS or a Dijkstra depending on the weight. And we could do the same by analyzing the input graph. And it's not currently done, but it is a possibility, yeah, for future work, definitely. Good point.
Okay, thanks.
Yeah.